Okay, continuing on with orthogonal sets. Okay, we have orthogonal projections. And we have for a non-zero vector v in Rn, decomposing a vector y and Rn into the sum of two vectors, one being a multiple of v, where we can just take the scalar multiple alpha, and so we have the multiple at alpha v, and the other orthogonal to v, and we will just refer to this as z. And we have with our equations, we have y is equal to, and we have the y with looks like the hat over it. That's the orthogonal projection of y onto v, and we have the sum between that and z. And for what we have, again, so we have that y is equal to alpha times v plus z. And in looking at what we have in writing, okay, so if I were to rewrite this equation, and we'll have the difference between y and the orthogonal projection of y onto v, and that is equal to z. And we have z is also equal to y minus alpha times v, and this is going to be orthogonal to v if and only if we have 0 is equal to the differences throughout. Okay, taking the dot product times z, so you have y minus the projection dot v, and you have the dot product between z and v, and you also had the difference y minus alpha times v dot product with the same vector. And once you follow through, okay, so again, so just distributing, so you have the dot product between y and v, and you have minus the dot product between alpha times v and v, and then taking the associative property, just shifting the parentheses around the two v's. Okay, so this will come down to the dot product between y and v minus alpha times the dot product between v and itself. And again, so you have orthogonal if we have this difference to be equal to 0, and taking what we have at the opposite ends and just switching it around with the commutative property, we have y dot v minus a times the dot product of v and itself is equal to 0. And if I put the scalar alpha by itself and isolate, okay, so we have canceling out the negatives and dividing between the dot product of v and itself, turns out that alpha is equal to the dot product between y and v all over the dot product of v and itself. And again, we have for the projection of y, okay, and there'll be some notations that we have here. So again, we have for sort of a projection of y, so you have this looks like PROJ subscript L of y, and this will be the orthogonal projection of y onto L, where L is going to be the line that runs through the origin, and we have is equal to alpha times v. And again, we have taking what we have in the dot product terminology in reference to the scalar alpha, you have y dot v all over v dot v times v. And we have coupled with the projection, we also have that the distance from y to L is going to be the length of the perpendicular line segment from y to the orthogonal projection, and is denoted by, okay, so you have the distance from y to the line through the origin, and we have is equal to the distance between y and the projection, and again we have is equal to the magnitude of the difference between y and the projection concerning it. And now for the formulas, okay, looking into application, and say we have y is equal to 2 by 1 vector where we have 1 and 7, and we have v is equal to -4 and 2, and we have, first of all, given these two items, it says to compute the orthogonal projection of y onto the line through v and the origin. Okay, so for the necessary ingredients, okay, so we'll be looking at the dot product between y and v. Okay, so first of all, we have the dot product between 1, 7 and -4, 2. And so for the dot product here, we have the value to end up at 10. And as for the dot product, the other ingredient we have between v and itself, Okay, so this will come out to 20. Okay, so again, just referencing what we have for the projections. So you have y dot v all over v dot v, and you have times v. Okay, so you got your y dot v at 10, v dot v at 20, and again for the given vector v, again that was at negative 4, 2. And we have 10 over 20 reduces to 1/2, and multiplying over negative 4 and 2, it turns out that the projection ends up at negative 2 and 1. And now, with the projection now determined, it says now to compute the distance from y to the line through v and the origin. Okay, so for the difference you have between y and the projection, so you have 1, 7 minus negative 2, 1, and we have 3, 6. And for the distance, okay, in this case, all right, so we have looking at the magnitude, so you have 3 and 6, and taking the squares and summing together, so you have 9 plus 36 is 45, and the distance will be the square root of 45, which can be simplified to 3 times the square root of 5.